Hello guys, in this video we will talk about activation functions in detail. So this is part 2 of the activation functions wherein I will talk about sigmoid, Tanh, ReLu and LeakyReLu activation functions. Okay, so let's start. We know that the formula for sigmoid is given as 1 by, so let me just write the formula, it's 1 by 1 plus e to the power minus z. So z is our input and this can be ranging between any numbers, right? Minus infinity to plus infinity. So it can have any inputs. But the outputs will be always between the range 0 and 1. So what it does, whatever numbers we give to it as input, we always have the outputs between 0 and 1. So this is what it does. And how do we implement it? So this is how we implement it. Return 1 by 1 plus mat.exp to the power minus x. X will be our input. And if you plot it, this is how it will look like. Okay. So exactly at 0th value, the sigmoid of 0 will be 0.5. Okay. So this is how the sigmoid curve looks like. Now, during back propagation in neural networks, we have seen that we will update the weights with respect to the loss at each layer, right? And to do this, we will have our chain rule applied and we will calculate multiple derivatives with respect to the outputs, correct? So initially it will be the output if we have 4-layered neural network. So it is like this. Then derivative of A4 with respect to A3, derivative of A3 with respect to derivative of A2. So it goes on like this, right? So what are all these derivatives? These are all the derivatives of our sigmoid. These are all the derivatives of our sigmoid function. Now, if you remember from the video wherein I was explaining vanishing gradient problems, the derivatives of the sigmoid function will be somewhere between 0 and 0.25. So the minimum value is 0 and max value is 0.25, right? And where it will be 0 for the larger values of input, large positives or large negative values of the input, the gradient of the sigmoid function tends to be 0. And at some point it will be 0 only. So what I'm trying to say, since we have the small gradients with respect to sigmoid, and if we have deep neural networks, we will end up multiplying small values multiple times, right? So what this will do, the end result will be much smaller, right? Then we will subtract this weight, this parameter from our existing weight. And this, if we subtract this value from the weights, the old weights and new weights will almost be equal. So we will not be able to learn further in our neural network. So our loss or cost will remain same. No matter how many iterations we do, it will remain same. It will remain constant. So we will not be able to converge to the minimum of our cost function. So this is what the sigmoid is and how the derivatives looks like and what's the problem with sigmoid function. So this is basically, we call it as vanishing gradients, right? Vanishing gradients. And since we have vanishing gradients problem, we will not use this in our hidden layers. We will not use this sigmoid function in our hidden layers. We will not be using sigmoid as activation functions in our hidden layers. So generally, where we will use sigmoid? Generally, if we are dealing with binary classification problem, the output neuron will have the sigmoid activation function. Apart from output, sigmoid activation function should never be used in any of the hidden layers. Okay, so keep that in mind. Okay, this is one thing about sigmoid. Now let's talk something about Tanh. It's short form for hyperbolic tangent. Okay, hyperbolic tangent. So what this does, we can also call this as a little bit improvement over our sigmoid. So how? I will tell that now. Okay. So what's the formula for Tanh? It is e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. So this is what tan h function looks like. And whatever inputs we supply as x to this function, the output will always be in the range -1 and 1. So see the difference here, right? So in sigmoid we had the outputs in the range 0 and 1, but in case of tan h we will have the outputs in the range of -1 plus 1. This also does one additional thing, which is centers the data around 0. Centers the data around 0, which means the mean of the outputs will be near to 0. And why this is important? In order to have the better learning in our neural networks, we always want to have the data centered around 0. Or in other words, we want to have the mean of the data that we are passing through the layers should be near to 0. So what this does, this will speed up the learning process. Speed up and it will be easy. Learning process will be sped up and it will also be easy. So this is what tan h does. So does this mean it is not having vanishing gradient problem? It does. It has vanishing gradient problem. So this should also be not used in hidden layers. Okay. So this also has vanishing gradients problem. Just like sigmoid, if you look at this tan h curve, so see the gradients are 0 or almost nearing to 0 once the values of the input tend to increase either in positive manner or in negative manner. Okay. So during this time also we will have the gradients which will be equal to 0 or almost 0, which are very small, and then again we will end up learning nothing. Our cost will not be converging. So this is with respect to tan h. Then how do we implement it? I have already shown it in my previous video. I am just refreshing it here. Okay. So this is how you implement tan h. Now one thing to note here is I told that tan h will try to center the data around 0. In other words, the average of the outputs of tan h will be near to 0 or 0, right? So if we just check the outputs mean here out from tan h, you can see it's almost 0, right? So this is almost equal to 0, right? It's minus 0.049, right? So this is one advantage of tan h over sigmoid. Okay. Now coming to ReLu. So what is ReLu? ReLu stands for rectified linear unit. Rectified linear unit. And what's the formula for this? It looks something like this: max of 0, x. So if x is less than 0, or in other words, if x is negative, it will return 0. Otherwise, whatever the value of x is, it will return that value. Okay. So how do we implement this? So it's simple: return max of 0, our input value. Okay. So this is how we implement, and if we plot it, you can see whatever the values which are less than 0, it will be converted to 0. Okay. So if I just want to clearly explain it, so the ReLu is something like this. So if it is x and this is ReLu of x, let me just change the color so that you can see it. So for the negative values of input, output will be 0, and for the positive values of the input, it will be as it is. If x is 0, output will be 0. If x is greater than 0, output will be x. If x is less than 0, output will be 0. So that's what rectified linear unit does. So this doesn't seem to have vanishing gradient problem. So this doesn't pose us with the vanishing gradient problem. Why? Because mostly we will only deal with positive values, right? And all the positive values will have some sort of slopes, right? Some sort of slopes. When I mean slopes, those are gradients, right? So we will always have the gradients. It will not tend to 0. That's one advantage of ReLu over tan h and sigmoid. But this poses a problem, a new problem called as dying neuron problem. So what is dying neuron problem? So if we have, let's say we have a hidden layer and we have multiple other layers here, and these are the neurons, and in this layer, let's say we have ReLu activation function applied. So what happens if the inputs are negative, right? If the inputs to these activation functions are negative, when I say inputs, let's take A3. How do we calculate A3? It will be, in this case we are applying ReLu of W3 into A2, correct, plus B3, correct. If this output happens to be negative, the activation will be equal to 0 and this neuron will be set to 0, and it is of no use whether if it's there or not there. Once it turns to 0, it's kind of switching it off. So it can be used as a switch. If you want to turn it off, pass in a negative value, it will be turned off. If you want it to be active, pass to it a positive value, right? So this is called dying neuron problem, and this 0 will be propagated as it is during forward pass. So it makes no sense to propagate 0, right? So this 0, since this is 0, if we want to calculate the activation at layer 4, this is again ReLu W3. Now it will be, input is A3, right? And A3 is 0, correct? It will be W4, okay? Because we are computing A4. This A3 will be 0, this will be 0, so we are just dealing with the bias now, right? If it's negative, again this will be turned to 0. If it's positive, then it will go as it is. So our values of these particular weights W4 will have no effects. So we will simply end up computing gradients for W4, update it for no use. Since this turns 0, the weight updation has no effect. So this is what is called as dying neuron problem. Okay, hope that is clear. And if you want to check the mean, it is not centered around 0. Okay, it gives some mean value because the data is not trying to center the data around 0. Okay, so now coming to LeakyReLu. So what is LeakyReLu? So ReLu as it stands for rectified linear unit, but LeakyReLu, why we call it as LeakyReLu? Because in case of negative values in ReLu, the output will be 0, but in this case we will have some small negative slope associated with the negative values, right? So this is given as, let me show it to you, the plot, how it is plotted. Okay, see, this is not flat on the 0, it has some slope if the input values are negative. So how do you implement it? It's simple. So instead of max of 0 comma x, it will be max of 0.1 x comma x, and this 0.1 is some constant and this can be varied. We can use 0.1 or we can use 0.01, whatever value we want to use. Okay, so what happens if x is greater than 0? We will always get x. If x is negative, we will have this multiplied with some small number instead of turning it to 0, right? So that's why we have this small sloped line towards the negative axis of x. So this is what LeakyReLu does. And does this solve dying neuron problem? We can say kind of yes. Yes, it does solve dying neuron problem, right? And does it have vanishing gradient problem? No, no vanishing gradient problem, right? So this looks to be a better choice if we encounter dying neuron problem with ReLu. But the widely used activation function these days is ReLu. But if we happen to encounter dying neuron problem, it's better to switch to LeakyReLu. Okay, so you guys now know how LeakyReLu works and how it avoids dying neuron problem. But still there will be a problem with this. Again, this will not center the data around 0. The mean of the outputs will not be 0. Okay, so that's what I have calculated here and displayed the output. Okay, now this, if you look at ReLu and LeakyReLu, it poses some common problem, right? So derivative at 0 at this particular input, it is not differentiable. Not differentiable. We cannot differentiate this. ReLu also, it's the same case with LeakyReLu. If the input is 0, it is not differentiable. So you have to keep this in mind, right? In order to solve this, there is something called as ReLu. I will talk about this in my next video. Okay, so this stands for exponential linear unit. Exponential linear unit. And this doesn't have this not differentiable problem as well. Okay, and this also speeds up the training in some cases. But generally, most widely used activation functions are ReLu and LeakyReLu in hidden layers. But one thumb rule for activation functions, it's just that never use sigmoid activation function in hidden layers. Never use sigmoid activation function in hidden layers. Why? Because we will for sure encounter vanishing gradient problem at one point of time during the training process. Okay, and the same applies to Tanh. So try to avoid using Tanh as much as possible as activation function in hidden layers, because this also has the same vanishing gradient problem. Okay, so try to use ReLu. If you are encountering dying neuron problem, go for LeakyReLu. If you are not happy with LeakyReLu and ReLu both, use some other activation functions like ReLu and other stuffs, which I will talk about in my next video. Okay, so hope these concepts are clear about these 4 activation functions: sigmoid, Tanh, ReLu, LeakyReLu, and I have also explained what is the problem associated with each of these activation functions and how one is improvised over other, right? So hope you guys like this video. If you like my content, please give a thumbs up and give some positive comments, and please share the videos with your peers so that they will also get benefited out of this. Okay, so till we see in the next video, happy learning. Bye bye.